Okay, so today we have Alexander Soloviev talking about hydrodynamics and transport near the QCD chiral critical point. So Alexander is an expert in orography and heavy ion collisions, and he did his PhD in Vienna in the Technical University, and then he moved to Stony Brook, and now he's back in Vienna again. So, okay, so when you want, you can start.
Thanks for the warm introduction and for letting me open this seminar season for you guys here in Santiago. I'm going to be talking about work that's ongoing with Adrian Florio, who's a postdoc in Stony Brook, and he's about to start a postdoc in VNL, so he's not going too far. Eduardo Grossi, who's starting a tenure track position in Florence now, so he's hopefully soon to be a professor. Eric Tini, I guess you guys all know, he's a professor in Stony Brook, and Fanglita Jan was a PhD student. He's now pursuing new directions in machine learning, so in New York. So he'll be the wealthiest out of all of us, I guess. And I'll be talking about work based on these 4 papers. This last one is just a proceedings of the other stuff, so more of like an executive summary. Okay, so to kind of set the stage, I'll be talking about the chiral phase transition and this little cartoon of the temperature against the chemical potential. And up here, when you're at high temperature and at small, say, chemical potential, you have this chiral condensate is 0, so you have exact chiral symmetry. And below some crossover temperature of around 160 MeV, this breaks and the chiral condensate acquires a non-zero value. And the kind of overall message of this talk is that chiral symmetry currently doesn't play a strong role in heavy ion collisions, and it should play a more important role, especially in application of hydrocodes, so especially in the context of soft pions, which I'll get to towards the end of the talk. Okay, so some more theoretical details of what chiral symmetry is, and especially in this hydro language that I'll be talking about. We have these conserved quantities, so the stress tensor and the isobector current, and this approximately conserved current, this isoaxial vector. So this is the PCAC that people talk about. The flavor symmetry is that eventually gets broken is SU2 left cross SU2 right, which I'll be referring to as O4. So this is just another way of repackaging SU2 left cross SU2 right. And so it's, again, like I mentioned in the previous slide, it's characterized by the formation of the chiral condensate, Q bar Q. And in the language of O4 physics, you'd have a vector. So this is this phi alpha. And the 0 component is the sigma. So this it has a 0 value when you're in the unbroken phase and has a non-zero value and acquires a non-zero value when you're in the broken phase. And the other 3 components are the pions. So it's kind of a neat way of packaging everything together in one vector. And in the chiral limit, when the quark mass is 0, this symmetry here is exact. And the pions are the massless Goldstone associated massless Goldstone modes, the pion mass vanishing. But the real world is messy and chiral symmetry is not exact. The quark mass is non-zero, and we have the pions are pseudo-Goldstone modes. In the context of what I'll be talking about, this mass term, the pions are non-zero, ensure that these Goldstone fields decay at very large distances. And we're going to be, and in this hydro language that was also developed by Son and Stefanov some 20 years ago, we consider this order parameter, this sigma, like a state variable. So very much the same like temperature or chemical potential. And just to stress again, chiral symmetry plays less of a role than it should in heavy ion collisions. Okay, so why do we expect that although chiral symmetry is only an approximate symmetry that's broken, why do we expect to see it at all in heavy ion collisions? And one piece of evidence in this direction is coming to us from the high QCD collaboration. So this O4 scaling that's seen on the lattice. So here I plot they plot rather the chiral susceptibility, which is the derivative of the order parameter with respect to the mass. Formulas are down here, and this is plotted against the temperature. And on the lattice, you can fictionalize the world. You can change the masses as you want. So this green line is kind of the real world, or the real lattice world, where the pion mass is 140 MeV. So this is the susceptibility. And what you can do is you can crank down the pion mass until it reaches, or as close to zero as you can get feasibly on the lattice. And here, this is the ratio of the strange quark to the lighter quarks. And this becomes, as this approaches infinity, the pion mass should go to zero. And you see that this structure becomes more and more peaked. And as a result, you have that the chiral susceptibility has this very nice scaling form that you can fit. And this is these solid lines here. And you see that the fit becomes, that the fit works pretty well in a lot of places. And it's a nice and compact way of extracting, first of all, these critical exponents, these betas and deltas, and goes to show that we should expect to see, at least from the QCD lattice, that the QCD lattice knows about the O4 critical point. So what do we do? Taking inspiration from, again, Stefanov in the early 2000s. We're going to be looking at hydro with a little bit more, hydro with some chiral physics. So kind of as a cartoon, you have these black lines. These are these equilibrated hydro modes. So this is all the other QCD effects, which are with momenta below the pion mass. And these red modes are the superfluid modes. So with momenta that are characteristically around the pion mass. And kind of at long distances, you expect QCD to behave like hydrodynamics. That's the basis of a lot of hydro codes and how people do a lot of simulations. And at finite quark mass, since we have this phase transition, we expect this theory to become superfluid-like for length scales that are approximately the inverse pion mass. And so the question that I'll pose today as well is, how do these superfluid modes, these pion modes, contribute to hydrodynamical variables in transport from the QCD hydrodynamics? And now I'll answer that question because time is short, life is short. And kind of long story short, if you compute, for instance, the shear viscosity, so we have a contribution coming from the QCD hydrodynamics, so from these black modes here, which is not what we're computing here today. What we'll get is a delta eta, so a correction which comes directly from these modes. And this is okay because you're doing, in effect, you're doing an expansion in the quark mass. So this is in which sense you have this hydrodynamic correction. And I'll go through the steps to how we actually compute this now. Okay, so the technical setup is we start from this effective Hamiltonian. We have the pressure, which corresponds to the QCD hydro fields that we don't consider in explicit detail. We have the O4 chemical potential UAB, and then we have a kinetic term for the O4 vector, and then we have a potential. So the O4 vector is something I already explained. It's just the condensate plus the pions. And UAB is the O4 chemical potential. So for instance, it's just a nice way of repackaging the same information that you would have if you had the axial and vector currents explicitly. So the zero I components are, for instance, the axial vector, the axial chemical potential, and the vector is the IJ, but anti-symmetrized. This potential here, we just take to be like a very simple quartic potential with an explicit breaking term, this H5. And we have this mass term, which we take to be T minus TC. This gives you the explicit break. This gives you the spontaneous symmetry breaking. And finally, for completeness, I also include that the derivatives here are charged under this O4 gauge potential, which we use to compute the equations of motion. Okay, and I'll be working in mean field. So just to kind of give a quick comparison to the lattice, how does our mean field approximation look compared to the lattice data. So mean field is really easy to compute. You just take your derivative of your potential that I showed on the previous slide, and you set it equal to 0. And then you find that all the pion components in your O4 vector, they go away because it's just a phase. And you're just left with these order parameters, these sigma bars. And then you know what sigma is as a function of the temperature. So for instance, here on this side, we plot the scaling function that people compute on the lattice as a function of temperature. And it's important to point out that this x-axis, I'll be using a lot, this variable z. And z is just T minus Tc. So at z equals 0, we're at the critical temperature. Below, we're in the broken phase, and above, we're in the unbroken phase. And you see that this is the order parameter that's plotted here. And you see if chiral symmetry was an exact symmetry, then you would expect that this order parameter would go straight down at Tc and become 0 exactly. But this is an approximately conserved. This is an approximately broken symmetry. So instead, you have this kind of smooth curve which goes down for large temperatures to 0. And you can see that in the critical region, the lattice and the mean field agree very, very well. And there's the right qualitative behavior both above and below Tc. Likewise, we can compute the masses of the pions and of the sigmas compared to the lattice. So kind of the pion mass, which is this dotted line here in the broken phase, so where you expect to have pions, it agrees really well with our mean field simplification. And the sigma agrees a little less numerically, but at least the minima, which describes where the pseudo-critical point is basically spot on. And everywhere else, at least the qualitative behavior is accurate. And yeah, just for completeness, the lattice results are by Engelsvogt and Karsh. We just extracted from those papers. Yeah, and so from mean field, you can just find the critical exponents directly and compare them to the lattice. And we see that there's a slight difference, but it's not too terrible. And basically everything that I talked about here, all of the pion masses, the sigma masses, they're all expressible in terms of this sigma bar or the scaling variable f. So everything will come down in the mean field. This is why it's so nice, because you just have this one function sigma bar, and basically everything, all of your parameters are a function of this. So that makes life a little easier. Okay, now we just need to grind the computation forward. You have this effective Hamiltonian. From here, you can compute the ideal equations of motion. You take the variation with respect to the metric. You take the variation to get the stress tensor. You take the variation with respect to the O4 gauge field to get the O4 currents. And you see, okay, you have ideal conservation, and you have this partially conserved axial current. So this explicit breaking term, this H, this is kind of in the language of O4 physics, it's kind of a magnetic field. But here on the right-hand side, this is just proportional to the quark mass. So if you send H to 0, it's equivalent to sending the quark mass to 0. So in this sense, the axial current is just partially conserved. And one other thing that we should do is we should make sure that the entropy is also conserved at ideal order. And we see that it's not. So this entropy current d mu s u mu, we compute and we see that we get stuff on the right-hand side. And what's kind of neat is you see that you want this all to be 0, and you have these two terms. And this first term here is just the Josephson constraint. So that the derivative of the phase is equal to the minus of the chemical potential. And in particular, this term here is the coupling between the pions and the chemical potential. So this kind of brings the whole system kind of interacting together. It's kind of neat. And that's just that ideal order. And so now what we do is we add dissipation. You just add some to the stress tensor, you add a dissipative tensor, a current as well. And to the Josephson constraint, we also add some dissipation. And okay, then we have to make sure that entropy is now no longer identically vanishing, but that it's positive. So entropy is being produced. And we find, okay, in the usual way of doing this, just to make sure as a sanity check, that we get a shear tensor, we get a diffusion tensor, diffusion term as well. And we also get some new O4 fields here. And this, for us, this sets all of the signs of all the shear viscosity, bulk viscosity of all the dissipative transport coefficients. Okay, and then I just flashed this for you. These are the full equations with the ideal piece and the dissipative corrections. So we have the relaxation equation for the order parameter. This is just the Josephson constraint with extra dissipative terms. Then we also have the partially conserved axial current, and finally the energy momentum conservation, where you have also the shear and the bulk viscosity making contribution, and there's also some bulk viscosity coming in from the O4 fields. Okay, so just to recap, we started with this action, we computed the ideal equation of motion, we added dissipation, but the equations are kind of bulky, there's a lot of components. So let's linearize the equations around mean field. So what that means is we just take our O4 field, we say that we have a condensate value and this linearized piece, and the pions are the linearization around this as well. So you have the sigma phi I, where the phi now is the linearized pion. And the equations become a lot simpler in this case, which is quite nice. So now the ideal piece is just, here you have, this is the Josephson constraint. So the Josephson equation with a dissipative term, given by a gradient of phi, basically. And likewise, the evolution equation of the time dependence of the axial chemical potential is also given by phi, as you would expect at ideal order, but also with some gradients of the chemical potential. And what's interesting at mean field in this linearized regime, the condensate decouples fully. So it's just a diffusive equation of motion. And all these parameters, this g squared, which is the pion velocity, m squared is the pion mass, gamma d naught, these are dissipative constants, and m sigma, they all depend on the mean field value. So in effect, they just depend on temperature in this linearization. So that's a very handy and very simple way to handle things. And yeah, just the slide is really basic, but this is just to get the notation the same, to get everybody on the same page. But yeah, I'm just going to talk about how we label propagators. If you look at the condensate equation, you can add a fictitious source, and from there you can compute the retarded Green's function. So we call this G R sigma sigma because it's the sigma sigma propagator. And what we'll need for when we compute the correction to the transport coefficient, to the shear viscosity, what we'll need is the symmetrized propagator, just a technical step. And that's just given for your consideration here. And for the coupled equations, we also have the symmetrized propagator, and I just call this G phi phi, phi mu, mu phi, mu mu. Okay, so that's just kind of a notation slide. And so here's one of the intermediate results, which I think is really neat. So this has a very impressive title. This is the spectral density for the axial charge density correlator. This is basically the symmetrized propagator that we computed in the previous slide at linearized order, but you then multiply by frequency and by this the susceptibility, the static susceptibility, omega k squared, and that's this y-axis here divided by the frequency. And this is plotted against the frequency as well. Okay, and this is kind of a complicated looking plot, but what we're doing is we're plotting for different values of z. So if we look at z equals 16, it's this central peak here, right? And that's just a diffusive peak. We're talking about a spectral function here. So we're at z equals 16, this is just to remind you, z is t minus tc. So this is when t is much larger than tc. And we have a diffusive peak. And we interpret this as the diffusion of quarks. So for the details are down here, by the way, for the equations, if you want to see what it looks like in the various limits. Likewise, if we start bringing the temperature down, since we have full control in mean field, we see that the peaks, okay, the cursor's a little slow for me. So there's the peak here that starts to get lower and lower as we decrease z. So eventually you start to form two bumps once you get below TC. And for z much smaller than, so for z much smaller than 0, so z equals minus 16, you have these really well separated peaks. And since these are really well separated, you can kind of identify them as propagating modes. And we can identify these guys as pions. So what's kind of neat about this is just in our model in this, just in the simple coupling between the chemical potential and the pions, you have kind of the whole story of this kind of hydrodynamization from diffusion to pions just in the propagator. So that's neat. And another way of viewing this as well is it's just a side note. So these two plots are, you should kind of view them in the same way. But this is the plot of the denominator of the propagator. So just looking at the pole structure. And here I'm plotting the imaginary part of the frequency against the real part. And you see that this diffusive peak, you actually have these two modes, one mode which comes from 0 and one mode which is the diffusive peak. And they actually come and collide at the point where you are, when you're near the critical point. And then they move away. And so from here, you actually see directly that this change in the space transition that you have is actually entirely seen in the complex plane. And it's kind of a neat little story, a neat way to view these same results. Okay, yeah, sorry. So that was a little diversion just to understand the form of the propagator. But in any case, now that we've gone through this whole recipe, we can now compute the change in the transport coefficients. So what we're doing is we're computing loops, and I'll go into detail about how we do this for the shear viscosity. We also do this for the isobector conductivity, but I'll provide fewer details there. But basically, okay, you have this loop. This is TXY, and you have the symmetric propagator. And the Kubel formula is here. And at linear order, we'll need just the contribution from TXY without loss of generality, which is taken in this direction. And we see that this actually decouples. So we'll need a sigma contribution, and we'll also need a phi. So here I have only one diagram, but you'll also need the sigma loop. But they're luckily both pretty easy to compute. So this breaks up the computation into integrating over two momenta here. So I just show only one of these integrations. So the pion correlator, so this G5 sim is basically capturing all of the dynamics that were in this plot here for various temperatures. And you just do this, the usual computation that you do. You just have the phi propagator, you have the momenta, you square it, you integrate. The only complication is that there's a divergence in the momentum, as you would expect. And but this divergence can be absorbed, and because we're computing a correction to the QCD hydro, so that correction just goes, the divergence just goes into this redefinition of your QCD hydro shear viscosity. But then you also have a subleading piece, or you have a finite piece, which is this delta eta, and we get this correction. Now we have this computation, we can do this analytically, but it's a huge expression. It's just better to show a plot maybe. So here is the correction of the shear viscosity as a function of this z, so t minus tc, normalized against the value at the pseudo-critical point. There's an infinity here, which I don't know why there's an infinity, but this is the notation we use. And so the complete correction is given by this green line here. And I can talk about the two different limits. So what we can do is for really large temperatures, so when we're in the unbroken phase, so we're really far away from the chiral phase transition, we can compute the same shear viscosity correction. And what we find is actually it's a very simple form because there's no pions or anything like that. So delta eta is just given by the sigma mass basically times the temperature. And that's this orange dotted line. And we can extrapolate from, this is basically at Z infinity, down to the critical temperature, which is at Z equals 0. And you see that the correction goes pretty well until you start to get really close to the critical temperature, and you suddenly have, it suddenly turns away and doesn't agree with the exact result. Likewise, we can go in the broken phase. We can compute this dashed line here, this dotted line, using pion kinetics. So now you forget about everything about the phase transition. You just say you have the Boltzmann equation with pions, and we're actually in the RTA. So the collisions are just in this very simplified form. And we're just moving in this kind of background. So you have this pion distribution. So you have a bunch of pions, and there's this fluid, this QCD fluid, which is this metric g mu nu, with this v squared as the pion velocity here. And you do the same computation, you can compute the shear viscosity, and you see that it agrees pretty well for quite a lot of values, but in the critical point, there's a huge mismatch. And so our result kind of nicely extrapolates between the two directions. And this red point here is just to give you kind of a feeling for how big this contribution is. Well, in units of 4 pi, the shear viscosity by the entropy density, it's around 0.3. So not an enormous effect, but still, it's not completely negligible. It's nice that it's not 10 to the minus 6 at least. But okay, and likewise, we can do this for the change in the conductivity. It's the same thing. We just have to, yeah.
So the previous,
Yeah.
So this is the correction to the shear viscosity
Yes.
divided by the uncorrected value.
That's divided by this value here. This should line up, I guess. It's -1 to 1. So this is the pseudo at the pseudo.
My question is, how is this correction relative to the uncorrected result?
Yeah, here. So for instance, if in the uncorrected result would be like 1/4 pi, say.
Yeah. Okay.
And this would be 0.3. Something like this.
Because I was understanding that it was of the same order because it's
No. It's less. Yeah.
okay.
Yeah. Okay, and likewise, we can do the same story for the isovector conductivity. And here you're just computing the current correlators. And here's the current. You only have a pion contribution. This integral is the same. It's the same story that you have this divergence, which you have to put back into the physical isovector conductivity. And yeah, you also get this result here. And it's just kind of funny. The only thing that we kind of noticed, which was interesting, was for the isovector conductivity, it's the same story. So except that the place where in the shear viscosity, this kind of works really well, that around TC, you suddenly have the divergence between the two descriptions. But in the isovector case, you can do the same story where you compute the large temperature limit and the pion kinetic limit. But this breaks down somehow still in the regime where you're in the broken phase. And yeah, okay. And yeah, then we can also compute this isovector conductivity, and we find it's around 0.5. This is correction.
So that means so you get eta over s equals 0.3 over 4 pi.
Yeah, the correction.
Or 30%.
Oh,
Yeah. Yeah, roughly. Okay. So much about that was all about mean field. Then there's we have also a new paper where this is with Adrian Florio and Eduardo and Derek, where we study the previous model but on the lattice. So
the corrected value is how much? I mean, or it's outside this.
sorry.
So the uncorrected value is 0.
Yeah, so we don't compute the zero order because
okay.
that requires other people.
Okay.
Yeah, so we can only do it as a correction too.
Okay, you're expanding.
Yeah.
But somehow you were assuming that it's the order of 1 over 4 pi.
Yes, something like this. Yeah. Yeah, so we can also put this stuff on these equations on the lattice. And I just show one quick result from this because I think otherwise I'm talking for a while. But yeah, basically you have these are the ideal terms. You have the viscous terms here, and we also add some Gaussian noise. So that balances out the viscous part. And what we are looking at, so here I plot the scaling function as a function of temperature, or as a function of T minus TC. And what we're going to be interested in doing is numerically simulating 5 points of interest. So one is at Z is 3.87. So this is at in large, like in the unbroken phase. Then the susceptibility has a peak. So it doesn't diverge, but it has a peak at this temperature here. And that defines your pseudo-critical temperature. So this is at Z equals PC. Then we're going to go a little bit away from the pseudo-critical point down to 0.7 times the pseudo-critical point. We also compute at Z equals 0. So that's where T is equal to TC. And then we also compute at very much in the broken phase. So when the temperature is much smaller than the critical temperature. So with Z is equal to minus 2.2. And further, we also can vary. We have two parameters to vary. So here, this is a plot of the temperature, but we also have the magnetic field. And that's in the 04, in this language of Halperin and Hoburn, it's model G. They call it, you can describe the quark mass as a magnetic field. So for us, we just refer to it as H. So we have H is 0.03 for all of these cases. So we have explicit breaking. But at the critical temperature, we also do a scan along different quark masses here. So we take different values. And the reason why we do this, it's a little cut off on the screen here, but it's to extract the dynamical scaling exponent. So going back 30 years, Rajagopal and Wilczek foresaw everything and did all of all the theory exploration and predicted that the correlation time, so the scales like the correlation length to some exponent. So this is zeta, not to be confused with the viscosity or anything like that. And this goes like the spatial dimension over 2, or just saving the trouble, it's 1.5 in the case we considered here. Just a little cutoff. And
So with magnetic, do you observe or do you get magnetic catalysis with magnetic field? Catalysis of
I don't know. No, I don't think so. I haven't looked at this. Yeah.
enhancement of kerosene debris.
You mean with changing age?
Yeah.
But we only do the scan at the critical temperature, right?
Okay.
So it's, yeah, we don't have enough data on this. So, yeah. So yeah, I mean, with our simulations, what we can do is we can compute all of the correlators. So here I have the axial correlator, and you see for so at this is at T equals TC. We have the different values of the magnetic field, so of the quark mass, and you see that the curves all start at 0. They all have different peaks and they're ordered. So you kind of expect that there's the scaling ansatz as well. And what we find is if we rescale the x-axis by 1.47 times constant, that all the curves fall on top of each other. So numerically, what we're finding is that this dynamical scaling exponent agrees with the prediction from the theory, more or less, so within some error bars. But that's more our fault probably than the universe's. Okay, and so I'm getting ready to finish. I want to talk about the outlook for experimental data. So especially solved pions in experiment. So here I take this panel from, usually it's like a triptych. Usually you have also other particles here, kaons and protons. But this is just from one paper, and many different analyses see the same kind of thing. So just for the, I'll just talk about what this plot is. So you have the yield of pions, which are these different squares for different centralities. And you have these black lines, which are the hydro fit. And when you look at it on kind of in the top panel, it looks like the fit is pretty good. And it is for a large amount of transverse momenta. But what we see is that there's an invariable pickup at small pt, where the data compared to the model doesn't quite agree. And people that we've talked to say it's hard to resolve this by just using hydro models. So it's kind of a place that we see that you need to just add some critical phenomenon in order to understand better this discrepancy. And to that effect, we did a very quick calculation. It's very crude, so I apologize for this. But what we want to do is we want to fit the dispersion relation of the pion for this region of small pt. So we expect that the soft pions are important between these 2 points, and then we don't want to spoil anything up here. So okay, we stop at pt equals about 1, so that's the cutoff up here, say, and we'll need, in order for the dispersion, we'll need the pion to model the pion velocity and also the pion mass. And we know from lattice that the pion velocity, and we know the pion mass as well, at at pt equals 0. So this is around 0.22. And we also know that at large temperatures, we want just pions to be free streaming. So we don't want the pion velocity to be anything different. So we don't want the dispersion to be modified. So we want this to go to 1. And yeah, we can then try a few forms. So I mean, there's the ideal hydro is just the ideal chiral hydrodynamics. You just have the velocity is constant with momentum. Then you can also do some second order chiral hydro where you have quadratic correction, and then you have to introduce a cutoff. So this is this lambda squared. And also you can, what we do in our paper is you have a point here, you have a point at infinity, and you just have some tanh basically that fits, or some polynomial that has that can interpolate between these 2 points smoothly. And then, I mean, we do this for the pions. We have to make an estimate for the pions in this, for the pion velocity in this way. For the pion mass, has a similar kind of ansatz. And then we just compute the yields using this really simple computation. And what we find, so here is just a piece of the previous plot that we have. So this is, again, back of the envelope calculation, so it shouldn't be taken too seriously. But what we find is that this ratio of yields of the pion fields to what you would expect from vacuum, so without any chiral critical physics, actually has this enhancement at small pt. And we can do this for different values of cutoff. So, okay, having trouble with the pointer, but these are just 2 different curves, one for cutoff at around 0.8 times pi t, and one at 1.2. We see that the vacuum values, so if we really didn't have this physics, it all goes to 1 at late points. And we see that this is kind of in the right ballpark. And when we were doing this computation, we were just trying to see whether this would be a million, whether this would be in the wrong direction. I mean, so we were kind of, I mean, the fact that these numbers are really similar, it's kind of crazy. So this shouldn't be taken too seriously. You need to do more work in this direction and do things more.
But the shape is different.
The shape is different, right? But it also, so you don't see it, but it's like, this doesn't go all the way to 0 as well. So we don't have the data down to pt equals 0. But in any case, you're right. Yeah, the shape is different, and we don't consider scatterings of pions as well that form. So there's modifications that need to be made. So what we can do is we need data from the lattice, so we can constrain the dispersion better. We can consider second order hydro and include also, like I just said, the higher resonance decays and pion scatterings. And kind of as a final outlook, there's this update to this inner tracking system. So this ITS3 now at Elise will allow, has a better resolution for low PT. And our hope is that this will see a lot more pions. And from there, we can maybe get more of a clear understanding of whether the chiral phase transition is actually observed in heavy ions. By, for instance, we can take a look at the multiplicity of the ratio of charged to neutral pions at small pt, or look at the correlation functions between charged pions. And yeah, with that, I finish. So thanks for your attention. If you have questions?
Okay, so any question? No.
Yeah, just one question. So basically what you're seeing is an effect that tries to you stick the low momentum pions together, so you get more
Yeah.
momentum pions. Can this be mimicked by the pre-cells? Because finally the pre-cells that you turn everything into particles.
Mhm.
Can this not be mimicked into some different pre-cell?
Potentially, yes, but we think that there's actual physics there.
No,
to
no,
just-
no, no,
Because as in like if you're, so if you have this collision and you have very slow, the temperature, so the core gluon plasma is expanding, you expect at some point that you're passing, you're transiting the chiral phase transition. At that point, you just have pions, right? They just fly away very slowly, but so I don't know how you would
yeah.
change your freeze. You mean to change the surface somehow, the geometry? Yeah, it's possible. Yeah. As well.
I mean, actually, the Cooper-Fry, whatever is kind of a prescription,
Yeah.
which immediately you get particles free stream.
Yeah. Yeah, okay, but then how do you define this curve? Then it becomes really hard.
Yeah, no.
Yeah.
I'm not claiming that there is no fitness in this or in that.
Yeah.